A linear equation can be used to represent a set of bivariate data that has a linear association on a scatter plot. In a previous video, scatter plot data was collected by dropping a ball from the top of a building and measuring the speed of the ball at different times before it hits the ground. To collect this data, a speed detector is placed on the ground, directly below where the ball is dropped. When the ball is dropped, a timer is started. As the ball is falling, the timer is stopped and the speed of the ball is recorded using the speed detector. Each time the speed is measured, two related values are recorded: the time that the ball has been falling and the speed of the ball. This bivariate data is organized in the columns of a table and represented as points on a scatter plot. Because the data points seem to form a line on the scatter plot, a line of best fit can be plotted to describe the speed of the ball as a function of time. Notice that some of the data points are above the line of best fit and some of them are below the line. This makes sense because conducting experiments always involves some amount of error involving measurement. Equations for the line of best fit can be used to predict the outcome of an experiment. For example, the equation for the line of best fit for the ball dropping experiment is S equals 32t plus 0, or just S equals 32t. Notice that the vertical axis intercept for the line of best fit is 0. Also, notice that the slope of the line of best fit is the change in the speed divided by the change in time, which is 32 and the coefficient of t in the linear equation. Next, the line of best fit can be applied to predict the speed of the ball at a given time. For example, if t equals 0.5 seconds is substituted into the equation, the speed of the ball is calculated to be 16 feet per second. The equation can also be used to find the elapsed time for a given speed of the ball. For example, if the ball is traveling at 40 feet per second, this value can be substituted into the equation. Then, the equation can be solved for t to determine that 1.25 seconds after dropping the ball, the speed of the ball is 40 feet per second. The vertical axis intercept for the line of best fit must make sense for the set of data being represented. For example, the line of best fit for the speed of the dropped ball data must have a vertical axis intercept of 0 because when the timer is started, the ball is dropped and not yet moving. So, at time t equals 0, the ball is dropped and not yet moving, so the speed of the ball is s equals 0. Compare this to the experiment where the ball is thrown downwards at a speed of 10 feet per second at time t equals 0. For this experiment, the line of best fit for this data must have a vertical axis intercept of s equals 10 feet per second, because this is the speed of the ball when the timer is started, t equals 0. Notice that the data for both experiments have a line of best fit with a similar slope. For example, when the time that the ball drops increases by 1 second, the speed of the ball increases by 32 feet per second.